STG and HP as well.
Right? Then we will pick up
Can I compare it?
which was something like here, right?
Right here.
Right, thank you. So, now, some of you did those sample questions a few slides ago, right? Actually, no, I think not all of you did those because there's actually fewer here than there was on the rainy night. I'm not sure how that works, but okay. Any questions on those? I mean, they were pretty straight ahead. You did those, right? So now when they show up on the museum, it's easy breezy, right? Cool, okay. So then any questions? So then we moved ahead, we talked about signed numbers, and we talked about subtraction, and we talked about these adders, subtractors. And any questions before we go on? No, you said no. I'm sure you're not bashful, you just say something else. Okay, so we've done addition, we've done subtraction, we've worked with signed integers. The next logical thing that happens logically is to talk about complements, right? So, wait a minute, we already did that. We already did complements. Why am I talking? Talk about that, talk about that. Signed integer, there we go. Okay, I think that's where we're going to talk, isn't it? Right? I remember talking about this, but we came here and I said, no, this is more than the 3 minutes we have to do. Right? So signed complements are written. Oops, look, we did that. So much for memory. This slide here. This slide here. We didn't do this one, right?
No.
Is that what we're talking?
We just started.
Okay. So overflow detection. So just kind of remind ourselves where we were, right? We're talking about, sure, there's every bit by itself. Remember that discussion, every bit by itself. And we can worry about single bit addition and signed integers and the same thing as subtraction, and we know about overflows and we've got to carry forward, all that good stuff. But the problem is that we seldom work with just single integers, right? So to understand it better, let's first worry about the logic, the equation description of it. So we have c to the sub n and c to the sub n minus 1. So we can show the carry in and carry forward, right? Remember, that's our two annotations that we're using for carry in, carry forward. CN is the carry. Yeah, 50-50 chance of this one, right? You have C to the N and C to the N minus 1. One is going to be carry in, and the other is going to be carry out. So C to the sub N is carry out in. C to the
Wait, it doesn't make sense.
C
C to the N would be carried out.
Yeah, so some of our earlier slides was we had C to the N sub N and C to the sub N plus 1. C to the N will be carry in. But now what we're talking about with the signed integer, because it could go either direction on us, right? So C to the N, well, in this case, we use carry out. C to the sub N minus 1 is not what we're carrying in. Or carry. C to the N could also be carry over. Okay, so the idea being here then, that I have some number, right? And I want to add these digits to those digits, and what the string up above it is, which is not a number, is my carry, right? So 1 plus 1 is going to be 1, right? Why do I show a carry bit there? Is there a carry bit for 1 plus 1?
Yeah.
Yeah.
The sum
One.
is 0, but the carry is a 1
Exactly.
because it's a 2.
Excellent. So, okay. So then 1 minus 0 is going to be 1. 0 minus 1. In this case, since I have a carry in, it will be 0. And 0 plus 0 is 0. Okay? Now, in the case of the overflow bits, all right, and I think probably an easy way to see this, go ahead and jump down to the description of it, and that is the way we would calculate an overflow bit is that it would be set in the exclusive OR case of either carry in or carry out, right? So if you have a number carried in, or if you're generating overflow, then you've got an overflow case. That's really the easiest way to describe that. So having said that, with 0 carried in, I have 1, 1, 0. Okay, I'm not creating an overflow, right? 1 minus 0, same thing. 0 minus 1, I do in this case. So I have to use that logic to concern myself with the carry in as well as any overflow generated to determine whether or not I have detected an overflow. Because that's the two conditions that can generate an overflow bit set. It's pretty obvious, of course, to see the one where we generate one, but if we're operating on two numbers that carried in number, it too also had an overflow condition. All right, so let's look at this with two real numbers there, okay? So 70 plus 80, obviously that's 700, 750. Wow, that's not so obvious. Obviously, it would be 150, right? So 70 in binary form would be this representation here with 1, 0, 0, 0, 1, 1, 0, whereas 80 is this 101, 0, 0, 0, 0, 0. Okay? So I want to add these, right? So how do I do that? Well, I said it's pretty straightforward. I got 0, 0 is yielding 0, 1, 0 is yielding 1, 1, 0 is yielding 1, 0, 0 is yielding 0, 0, 1 is yielding 1, 0, 0 yields 0, and then comes the interesting one, and that is 1, 1, which will generate a 0, but also create an overflow, right? Because it's now larger than this current number. Since the most significant bit was used in representing 70 and representing 80, obviously when I go to 150, there's going to be an overflow, which is exactly what that shows, with the 1 and 1 and the most significant bits being added together, generating 0 and generating an overflow. Right? Pretty straightforward to see. But now let's take a look at a different pair of numbers. They look similar, right? They're just half as large, right? I, in this case, have minus 70, and I'm going to add minus 80 to that. So obviously the result's going to be minus 150. Okay? So in this condition here, with the minus, I'm going to set my sign bit, right? I'm going to set my sign bit to 1 that shows it's negative. Which form is this in? What are the two possible forms this negative number could be in?
1 or 2.
1 or 2. So 2's complement and something else.
2's complement or 1's complement, right? That's our choices. So looking at that number there and looking at the value there, what do you think that representation is?
One's complement.
You think it's 1's complement because?
Because the negative number would start off with a 1 if we need 2's complement, right?
Right. It would start off with the MSB bit set, and then it would be 1. It wouldn't be 0, right? It would be 1. So in this case here now, I've got 150. Well, let's go negative 150. Let's go back and look at 150. Here was 150. We said it was 1000 minus 70. I'm sorry, positive 70, right? Is 1000 110. Now we're saying a minus 70 is 0 111 010. We have a suggestion on the floor that we think this is a 1's complement because we started after 1. And does that seem to support that? if I took, no, I'm not gonna say.
It's 2's
What you observe. Okay, let's take an easier number. Let's look at 80. There's 80. 101, 0, 0, 0, 0. Negative 80.
It's 2's complement, right?
So now we have a proposal that we think is 2's complement. Why do we think so?
Because if we flip them and then we add 1, we get the, I don't know. Because if it was if it was like 1's complement, you just flip them, right? So at the end you will have a 1 and a 0. Am I not-
For 1's complement, I would flip them.
Yeah,
And the 1's in the 2's complement, I would
add 1.
add 1 and start from
Start from 1?
1, right?
Wait, am
So if I
getting-
started from 1, would it be larger or smaller than a positive 80, ignoring the MSB? The sign bit. If you ignored the sign bit, totally ignore the sign bit, of 80 and minus 80 in 2's complement, what would those two numbers look like? How would they be different? You're close. Yes,
The negative number would be 1 bigger.
one bigger. Is that one bigger? Or smaller, excuse me, is that one smaller than that one?
I'm confused. I'm literally confused.
Let's write them out, so I'm flipping really fast here, right?
Yeah.
Positive 8 is 101,000. Minus 80.
It's 0, 1, 1.
What's that?
0, 1, 1.
We were gonna tell you.
Oh, yeah. 0, 1, 1, 0, 0.
Oh, you're good, you're good. We were gonna tell you the negative 80 so
Oh,
that you wouldn't have to walk.
Okay, great. Tell me what it's gonna be.
0, 1, 1, and then 4 zeros.
So which is bigger by how much?
So
I think positive 80 is bigger, right?
the 80 is bigger,
Positive 80 is bigger.
right? I'm telling you myself. Okay,
No,
that's
they're
80.
both equal.
So the thesis on the floor was that if I
No,
took
they're
my
both equal.
positive number
Wait, which one's bigger?
and I added my sign bit,
The 80 looks bigger by like 32.
say again?
The 80 looks bigger by 32 bit, right?
Yeah, it's quite a bit bigger, isn't it?
Yeah.
Right? Because it's not a matter of just adding 1 here, which still doesn't get you to 101.
No.
You've got all these bits here too, right?
Mm-hmm. Yeah, so 80 is bigger. Yeah.
So yeah, it's significantly different. So if it's significantly different, which number system representation do you think we're using?
2's complement?
Which one?
No, just a guess.
I didn't hear you.
2's complement?
2's complement, the one where we just add the sign bit and we start with 1.
Oh, no, no, right.
It's 1's complement.
1's complement.
1's complement where I start with all 1s and work my way down.
Gosh, I'm so
Oh.
confused.
The decimal. Wait, no?
Well, can I tell you why it's not
0's
2's
complement?
Sure.
It's not 2's complement because you're not just flipping the bits and adding 1.
Also, the signs are wrong with this 2's complement.
Say again?
The signs are wrong with this
The
2's
signs are
complement.
wrong, it's 2's complement, right? Okay, so now we have positive, go back to the negative. So I have negative 70 plus a negative 80. And since they're negatives, I've got my sign bits now set. They weren't clear as they were in the previous example. They're set, so they're negative numbers. So 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Ooh. 1 minus 1. That means I got to borrow from here. So I borrow that over here. So I set that to 1. That thing goes to 0. Making it negative 150 because we carried. how would we implement this then? Overflow detection. Okay, starting off with our very definition, right? We said that either C to the N, exclusive OR with C to the N minus 1 is set, then I've got to carry this here, I've got an overflow detect. Right? So that means coming out of my adder subtractor, I'm going to take C to the N minus 1, feed it through an XOR gate, and out pops V. Just like the expression now. Yeah, there, just like the expression said. Right? That one's pretty straightforward to implement. Now, in doing so, what we've done is we've introduced the term V because that's our overflow detect. But we still are concerned with C, so we're still going to pass C through because this next bit's going to need the C, right? So we'll go ahead and pass that through, but now we're generating V by passing both C and N-1 C again into this exclusive OR gate. Okay, so some practice time for you. All right, here's some slumps. Here's some sample problems. Okay, you've got unsigned binary numbers using 2's complement performing subtraction. Okay? The other one I want you to work on are these numbers. I gave you decimal numbers, so now you have a little additional work. You have to convert these to binary numbers, and I want you to use sine 2's complement for the negative number representations. Throw them through your adder subtractor and calculate the results. Yes, there are a whole bunch of free calculator websites out there. And there's free tools that you can download onto your own machines or phones. They're not going to help you on an exam. Since they're not going to help you on an exam, then I would say, sure, go ahead and use them after you've hand calculated these to see if you got the right answer. Okay? The same with the other slides that I'm hoping you did, even though you didn't raise your hand because maybe you were too scared I was going to ask you to walk us through it.
Yes.
I'll go with that definition, right? It makes me feel lots better. Really, 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 you need to be working these problems, and you do have a way to check your results, okay? So do these because it's not going to magically work on exam day. Okay? So those of you that are getting by, doing okay in classes and stuff like that, please note this is very, as you've already observed, this class is very different than a lot of the other CS classes you've taken so far. Okay, so it's going to take a little bit more attention by you and a little bit more exercises by you to prepare for these exams to get this material down, okay? So I want everybody to do well. Really want everybody to come out of work with an A. You earn an A, I'll give you an A. I don't care how many of you it is. All right. So other arithmetic functions. We can add, we subtract, we can assign integers. We've done 1's complement, 2's complement. Done complements. Okay, so another thing is contraction. Okay, what contraction is talking about is getting rid of redundancy. It's a way of doing simplification. Okay, so what you do is you put a circuit together and you're looking for paths that are adding absolutely nothing additional to the results. And that's going to be a redundant circuit. Okay, so that's really the basis behind contraction, what it is that we're really trying to do. Okay, so the circuits that we're looking at, of course, we're looking at incrementing circuits, decrementing circuits, multiplications, and we also have these other circuits called zero fills and extensions, which may sound obvious, but we'll go through some definitions here to make sure we understand. Okay, so designing by contraction now, that is, I'm designing circuits and I'm coming up with basic functions. I'm doing my K-maps. I'm laying out those circuits that I need to build. I then lay them out on circuit diagrams, okay, and now I'm looking for redundancies in my circuits using contractions, right, to reduce any extra circuits that aren't needed, okay? So to do that as part of the design process, okay, as a formal technique to do that, what we're looking for is logic inside of the functional block. So if I'm looking at a full adder, or an adder subtractor, or I'm looking at a half adder, whatever circuit I'm looking at, I want to look just inside that box. I don't want to be tempted to look outside of that functional box. I want to worry about one functional block at a time, okay? And what I'm going to do is, if I use that same block to implement a different function, okay, I want to build an adder subtractor from an adder, a full adder, right? That's an example. I can start doing that. It's just the thought process behind the design, right? I've already got my full adder, and I want to build my adder subtractor. So I started realizing that, wait a minute, I have to worry about this carry bit and a complement function, all that kind of stuff, but I can still use my full adder. So what you do is you start looking for the original function, you start adding simple functions to it to add the complementer, to add the overflow, okay, so I'm not the overflow, the carry in, and the carry out, okay, so you're doing that. And then what you're doing is you're looking at the circuit itself and its traces. Okay, so those logic diagrams you were looking at, you look at the traces, okay, because running zeros and ones using your probes, if you're doing software design, which is why we're using our tool, okay, so you put probes in there, you add zeros and ones in there, looking for your results, not just the equations, and you're putting them in there, and you're making sure that the results, based upon the data that you generated for input, are correct. Okay, if you take out a circuit, does it change it any? All right, so what this does is it eliminates guesswork, because you're using a simulator, a real-time simulator, to proof these circuit changes for you. Okay, as long as you're testing all combinations of inputs, this will work. If you're trying to take shortcuts and saying, well, let's see, I've got 5 of the 8 okay, I'll bet the rest of the 3 are good, your bet might be wrong, okay? So you're already taking a shortcut using the simulator as opposed to doing it all by hand, calculations and manipulations of equations. So do all of your different combinations of inputs and confirm your outputs based upon predicted outputs. Okay? And then, if that proves true, then you can go ahead and simplify it. Now, in your text on page 178, in this version, our version, version 4, we have a whole list of rules that you can actually walk through one at a time and confirm that they're true. Okay, so I don't want to go over all of them tonight because that's something we can go through if you want. But I give it to you there as a reference in page 178. There's a place to go to look at all those different rules for contraction and apply them. All right, so nothing like an example here to help us. Okay, so let's take a look in this case at the Ripple carry adder. Okay, using an N=3 for this particular case. All right, so what we're going to do is we're going to start off here up in the upper part with S sub 0 coming into our Ripple adder where we have A sub 0, which was what? What's A sub 0? We have 2 inputs. This is our Ripple carry adder. We have A sub 0 coming in, and we have C sub 0 coming in. What's A sub 0? What's C sub 0?
The carry.
The number you want to add.
What's A?
The number you want to add.
The number you want to add. And C,
The carry?
carry
In.
in.
Oh.
Yes. So I have the number I want to add, and then I have a hard 1. Why did I have a hard 1? Does anybody remember in a Ripple carry adder? Why do I have a hard 1 on S0? Bit 0.
Because B is 0, 0, 1. So that's the second number, the rightmost bit of the second number.
Yes.
How can we get B but not A? Just out of curiosity. We got B for this example, but we didn't get A.
Thanks.
Anybody?
Are you trying to increment A?
That one.
So here's our input. Incrementer is n equals 3. We're going to set b to 1. So why do we have 1 hardwired in here?
To increment
Say again?
it? To increment it by 1.
Well, I said set b to 1. Right? So I
Yeah.
have 2 inputs, A and B.
Mhm.
Right? So should I have labeled B?
We don't need to label it because you already know what B is. Oh, oh,
Yeah,
oh.
I don't need to. It would have been good form to go ahead and label B. So I would have had A sub 0, B sub 0, and also mentioned that its value was set to 1. That would have been a much clearer way to describe your input set. And clarity is always a good thing when we're talking about software engineering or any sort of engineering. Okay, so yes, that input I should have labeled that input B sub 0. This was, I won't say checking, but this was a case where, are we reading the slide, right? We said set B to 1. So take B, set to 1, and then I have A sub 0 coming in. And now I'm hardwiring C sub 0, right? Why? I didn't say any, I don't think I said anything here in my setup about C sub 0, which you all correctly said was carry in, right?
Yeah.
So why did I hardwire it to 0?
How could you have a carry in on the first addition?
That's an agreement.
Yeah, this is your first bit. There isn't anything to carry in, ever, right? So I can go ahead and hardwire that one in. But at least I did label it C sub 0. So I have C sub 0, hardwired to 0. B sub 0, which isn't labeled but should be, we said we want to set that to 1, and we want to add that to A sub 0. Okay, so then my ripple carry here, ripple carry forward. The rest of it is just like we talked about before. We have this setup case here. I've got n equals 3, so I'm going to go forward 2 more bits, right? That's what n3 says. So I've got my exclusive OR and going into an AND exclusive OR, which pops out S0 and then generates my carry out bit for C0, which is a carry in bit for C1. And we do the whole thing over again, but now for bit A1 and bit A2, and simply set B equals 0, 0, 1. B sub 1 is set to 0, and B sub 2 is set to 0 as well. We don't know what A1 is and A2 is, but they're going to come in and get added to 0, 0, 1 using these circuits. And this is all review, right? You can actually create these now on an exam, right?
Yeah.
Yes.
Thought so. All right. So now the question is, with contraction, can I do anything with contraction that will still get me the same results here? For this hardwired number, for this hardwired n equals 3 case. Okay, so what I'm saying is, in this case, I've got 1, 0, 0. Is always going to be added to some number A sub whatever. Okay? Well, in this case, it'd be A sub 0, A sub 1, A sub 2. So we look at this and we say, whatever A sub 0 coming in is going to be, S0 is going to be opposite of it, because B sub 0 is set to 1, right? And since the first thing it's going to do is go into an exclusive OR, if it comes in as a 1, it's going to pop out as a 0. If it comes in as a 0, it'll then pop out as a 1. So it's always just going to be opposite of whatever A sub 0 is going to be. And then we take that value and push it forward, possibly. That's what we're thinking would happen here, right? Let's take a look. So that we're using these binary probes now, right? Put binary probes on here. We just trying these test cases here. I have I gave a sub 0 was 0, and I'm adding it to 0, 0, 1, so it better pop out a 1 carry 0. Well, that's what that says. And it's no carryover, so that would be 0, right? If it was set to 1, and I added 1 and 1 together, okay, 1's going to get inverted to 0 because 1 plus 1 equals 0, and 1 would carry forward because it's a carry bit. Right? Look at that. Those 4 messy circuits, those 4 messy gates there, and all I need is an inverter? Why didn't we do that in the first place? Now remember, we're hardwiring an add to a 001, which is kind of, but it helps us to understand this contraction, right? So that's what we're looking at here. If that's the circuit I'm trying to build, to always add some 3-digit binary number to 001, this can replace that. And that would generate the correct results for B sub 0. A sub 0. Sorry. That creates the right answer for A sub 0 every time. But now we have to worry about the other bits, right? So let's take a look at A1. So A1 comes in now, and I've got my carry in bit here coming into my circuit, and I maintain that instead of those 5 gates, I can do this with just 2 gates. Let's see what happens here. So if I'm adding 0 to 0, right, and that means no carry in, and my result here was 1 because that was a 1, right? So I have 0 here, and I add 0 here. I have 0, 0. 0 and 0 is going to generate a 0, which is exactly what you would think for carry out, right? 0 and 0 is not going to generate a carry bit. However, if this was a 1, right, if I did try to add 1 to 1, and it generated the carry out bit, which is now my carry in bit. Oh, I'm sorry, we should have finished this one. If this was 0, this was exclusive OR was 0, my sum would have been 0, right? Which is exactly what we expected. Now, if I generated a 1 here, then I generated my 0 output here, but I also generated a carry out, which is a carry in. So now I have a 1 coming in here. I carried this in. So if A1 rather was a 0 still, right, then I would generate a 1 here. My carrying in bit would come in, added with the 0 would just generate a 1, which would be the correct answer, 1 plus 0 is 0. If I had a 1 here and I had a 1 here, then my result would be 0. 1 and 1 here would also generate a carry bit, just like we would expect. So those 3 conditions work just fine. And then all I have to do is worry about this last bit here. And this last bit, I really don't care about my carry out bit, right? Because I'm hardwiring it for this 3-digit number. So I don't care about carry out. So all I worry about is my sum bit. And the sum bit, the only thing it worries about is if 1, is this 0 and 0, because that's 0. Is either 1, 1, then it's 1. And if they're both 1, then it's 0. And I said I don't care about the carry out bit, so we're done. Yes?
And you don't care about the carryout bit specifically because there's no possible way you can add 0 twice and get a carryout?
That part is easy, yes. 0 and 0 is 0. And I don't generate a carry out, no problems there. The thing that's intellectually challenging to us is that if I have 1 and 1, if I had a carry in bit and I was adding that to 1, right, the answer should be 0 still, but what about that carry out bit that I would have generated? What happened there? Are we saying that 2 numbers are equal to each other? 0 plus 0 is equal to 1 plus 1? If I have 1 plus 1, I would have generated S2 of 0, but I would have had a carry bit in a normal circuit. But now I'm saying, I'm just adding these 3 bits. And all I'm worried about is how to simplify. Well, if all I have is 3 bits, and I don't care about anything larger than that, then yeah, I truncate, and I have to build into my design logic the case where 0 can equal 0. Okay? But if I'm happy with that, because I said I was happy with just 3 bits, then that's fine, because that means I'm really not gonna generate that last number. If I said I wanna generate something that works with 3 bits, I don't care about the highest order number, it'll never happen. That's the only time I would say a 3-bit circuit without a carry bit would be acceptable. So by design, I'm saying I will never have a number that is 8. Right? Or larger.
Yeah.
All the smaller ones will be properly represented here. And look, 4 gates. I had 5 in the first bit. Significant cost savings. So that's the whole idea behind contraction, is that, yeah, that's all correct. And once you do that, then you start doing your analysis about what your requirements are, i.e., I'm working with a hard-coded number 001 that I'm going to add to whatever 3-digit number, and I don't care about anything higher than 7, then we're good. Make sense? Okay. So that's what contraction is about. Now, the next thing, and then of course we apply that, that's a very simple example there, but you would apply those principles, that thought process, to other problems as well. Like I said at the start of the contraction discussion, you want to stay within that functional block that you are analyzing. Because if you go outside of that, then you're going to get too complex too quickly, and it's going to become unsolvable or untenable. Okay, and you'll spend hours and hours and hours working problems that don't need to be that hard. Okay, so you stay within your functional blocks and do your analysis one at a time instead of trying to look at everything completely all at once. You'll never get there. Okay? So next, we want to talk about incrementing and decrementing. Incrementing and decrementing are pretty straightforward operations, right? What does an incrementer do? Takes some value in and does what to it?
Increases the value.
Adds 1 to it, and there's your result, right? Well, incrementers could be a little bit more sophisticated. I think I heard somebody say this over here. Incrementers could be a little bit more sophisticated than that, is that you could increment by 3. You could increment by 8. You could increment by 12. You could increment by some other number other than 1. But that doesn't really change the way an incrementer works, because all an incrementer is going to do is going to say M is going to get N plus I over and over and over again. So every time you feed it an M, you're going to take that value in, you're going to increment it by whatever hard value this incrementer is working with, and spit out the results over and over and over again. Give it a number, it adds that number to it, and generates the result. Right? So it's always adding, oh, wait a minute. Doesn't that sound familiar? Sounds familiar. Anytime you give it some number, it's going to add some fixed value to it and generate a result. Right? Isn't that what this circuit just did? We're always going to add 003 to whatever number A is. It's an incrementer. Okay? With just 4 gates for those 3 bits. 1 gate had 5 bits, 5 gates, right? So an incrementer, that's exactly what it's doing, okay? And we just saw an example of that. And we saw how we could create a really low-cost version simply by using this thing called contraction. Decrementer, then, is going to be very, very similar to our incrementer, right? It's just that, well, it's still going to add, but this number is always going to be a minus value, right? Which tells us what? What does it tell us about the second value?
To be the same for both of them.
Who was talking?
It would be the same for both of them, just like subtract instead of add it.
Not quite. We're still going to just add them, right? But this value, we're going to do what to this value? Complement it, right? So we're going to complement this value using either 2's complement, 1's complement, and just add it to this number. There we go. And the cool thing about this is I don't really even need, well, it depends. If it's a hard incrementer, if it's a hard count incrementer, like I'm always going to take b equals 003 or 001 for 3, then I just build a circuit for it, and I'm done. I do that complement once, and I build it in hardware, and I'm done. But a lot of times we feed the complementer the incrementer value, in which case it's got to convert it by doing a complement, and then putting that into the increment decrement value. And then it's the same circuit. We just add these two numbers. Multiplication, however, is a little bit more fun. Okay? So we talk about a constant. That's exactly what we drew here, right? And that's why I came back here and spent the 13 seconds or whatever to change this from a little I to a capital I. Hopefully you recognize that, ooh, I changed that from a variable to a constant, right? So I represented a constant by a uppercase term instead of a lowercase term. And that's syntax there to kind of pre-gauge you for this particular slide here. Okay, so adding, subtracting, we saw that adding was pretty straightforward. We can build an adder circuit for an incrementer pretty easily with low cost. And I can use that same circuit then to subtract by just throwing the number to the complementer. Okay, but now I'll worry about multiplication. So let's take a look at this example here because it's always easier to see what's going on with examples. So what if I took some number b, 3:0 tells us what about b? B parentheses 3:0 close parentheses is telling us what about b? We had a name for this. Names are definitions. Definitions are exams. What does that up there say? B 3:0. What does that tell you? Yes?
Is it bits 3 through 0?
Yeah, it's bits 3 through 0. It's a bus or a subbus, right? So we have some bus with some number of bits on there. We're worried about bits 3 through 0. Okay, we're going to call that B. So that tells us there's how many bits? 4, right? 3, 2, 1, 0. Okay, so I'm going to build my multiplier by taking a 4-bit adder. I'm going to put my input bits B0, 1, 2, 3. And look at over here, I have bits 0, 1, 2, 3. Okay, and what is it I'm trying to do? I want to multiply it by 101. Okay? So if I take my 4-bit adder and I take my bits B0 through B3, okay, and I feed them into my 4-bit adder, I generate my sum bits, and I generate my carry out bits, I claim that I can create the results doing a constant 101 by simply taking the first 2 bits and letting them fall straight through as my carry bits. Okay? And then repeating this pattern here will then generate this 101 function. So let's see if we can visualize this and make some sense out of this. Oh, good, we're not at recess. Oh, look what I found, but it's way back here. There we go. Clean board and an eraser. All right. You thought that was a rag, didn't you? So, I have V3, V2, V1, V0. And I want to multiply it times 1, 0, 1. Yes?
Can you explain what you mean again by the V1 and V0 please?
That's what I'm doing. I'm trying to convince ourselves that this might work because this doesn't follow any logic that we've talked about so far, right? Because I'm sort of jumping ahead. Because I'm saying if I want to, by contraction, because remember, we're trying to design a circuit by contraction. And by contraction, I want to design a circuit that's hard-coded to multiply any 4-bit number by 101. So let's think about what that means first, okay? Let's take, I can use any number, but right now I want to use this representation, and multiply some 4-digit number by 101. Well, the results are going to be B3, B2, B1, and B0, right? Then I'm going to come down and say, oh, 0, 0, 0, 0. And then I'm going to come down and say, B1, B0, sorry, B1, B2, and B3. And then I'm going to add all of these up. Well, look what happens. B0 falls straight through. Look what happens. B1 falls straight through. Yes?
That's supposed to be B2, B2, B1. Supposed to be
0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. In this case here, they're all zeros because I'm multiplying this by 0, right? So B0, 1, 2, 3, 0, 0, 0, 0, B0, 1, 2, 3, B0 is going to fall straight down. B1 is addition. It's going to fall straight down. So I claim C0, C1 are going to fall just straight out. Now I worry about my adder. And I claim that I can use a 4-bit adder because, you're going to let me do that, weren't you? 4 bits starts here. And it's here. Okay? So now I have to add B2 plus B0. I have to add B2 plus B1. And yeah, B2 and B3 also fall straight out of here too. So really, I could probably get away with a half adder, couldn't I? Yes?
If you had to carry enough times, wouldn't it not fall through?
Correct. Because I ignored the carry bit here, right? So if B2 was 1 and B1 was 1, I would generate a carry bit. In which case, yeah, I'm sorry, I do need that 3rd bit to handle that carry situation. It could generate a carry too. Right? But we said that's our max number, and we don't care if we have the max number exceeding and generating a carry. By design, it won't happen. So that's why I need a full adder, not a half adder. So now you know how to answer that question if it ever comes up on an exam. But see here, what I need to do is I need to add these two numbers, worry about a carry. Add these two numbers, worry about a carry. Add this number to a carry if it exists, and add this number to a carry if it exists. And oh, by the way, if this generates a carry, this one's not. I mean, it's okay. So that should handle all cases here. All right. So what I did here is it said, Okay, so B0, B1 is going to fall straight through. So B2 and B3 I need to feed into here. And then I need to jump 2 and go to my B0, 1, 2, 3 because I'm taking two numbers. Remember, that's the way a 4-bit adder works. I have these 4 numbers are going to get added to those 4 bits. These 4 bits here are going to get added to these 4 bits here. I have bits 2 and 3, but I'm never going to have a bit 4 or a bit 5, so I hard-coded those to 0. And then I simply take B, 0, 1, 2, 3, add it here, and that's going to take care of this multiplication operation of a binary number times 1, 0, 1. Now it makes sense, right? So when you're presented with a slide like this, you need to go back to the fundamentals and remember what it is that you're looking at. Oh, a 4-bit adder, a 4-bit binary adder. And I'm hard coding the value that I want to multiply to it by 101. So given that definition there, by compaction, you can then take your 4-bit adder and simply realize that, yeah, I'm going to have 2 extra bits, but the first 2 bits are always going to just fall through. So let that happen, and with 2 bits and 4 bits, you can use a full adder, you're done. Right? You got it yourselves. Right? It's just a matter of using the tools that you have so far to solve bigger problems with by just doing a few extra steps, visualizing, if you know, what the problem is. Sometimes it takes working the problem through a little bit. Simple little multiplication, 2 binary numbers shows that there's some savings that can be had. Any questions now on multiplication by constants? Yeah.
For the bit in the seconds place, did you need to put B2 plus B1 plus
This one here?
Yeah.
That's what I have here, yeah.
The up above, the B2, is that supposed to be B2 or is that B sub 3?
Oh. Oh, that's what you're saying. I'm sorry, you're right. Thank you. Both, yes. That actually makes a lot more sense. Yeah. Other questions, multiplication, constants. Okay. Next thing coming up is the zero fills. So zero fills, some would argue, are not important, but those that would argue that don't understand how binary numbers work inside of a system, what we call a stochastic system that needs to be able to generate predictable outcome numbers, which is what we're trying to design here with these circuits, okay? Because from a math purist point of view, which is one of the reasons why we're now in our own department and we're not part of the math department anymore, because this really annoys them when we do stuff like this, right? So, okay, so from a math purist point of view, that is correct, right? I can add those two numbers up, and I'm going to generate some number like that, right? And they're happy with that. They're pleased with that. They say that's always the same thing. And we're saying, wait a minute, that's different. We say that those two numbers are different. And like I said, it gets them a little annoying. Somebody formed their own department. But anyway, there's more to it than that. But this is important because every bit has to be taken into calculations. And we cannot guess at bits. If we start guessing at bits, one of the times we guess is going to be wrong. And if one or more times that we guess is wrong, then we're going to start generating all kinds of incorrect results, which will just snowball on itself, and people will run us out of town and say, we'll never hire you again for anything. Or we'll never let you come back and speak at this conference. I don't care who you bring with you, or co-author your paper with. Okay? Those two are not the same because, as we saw in our K-map stuff, right? These 2 bits we're claiming are unknown. Mathematicians are perfectly fine because they say they don't exist. But for us, they do exist and they're unknown. And if they're unknown, then that means the results generated by those 2 bits, whether they're zeros or ones, are going to generate results here that we don't care about. We say it won't change our answer. But we know if we change this to a 1, it will. We know that if we change this to a 1, it will. We know if we change both of them to a 1, it will. And since the hardware circuits that we're going to implement in our adders will add those bits regardless of whether they're set or clear, it's going to generate results. Is it a predictable result? If we say we don't care, it's not predictable. And those bits may get left over from a previous operation where they were set, in which case we'll get the wrong answer, in which case that's just bad, bad, bad. So, sometimes we have to do this thing called zero filling, okay, where we say these bits need to be set to 0 for this next operation, okay? So we have a couple of different scenarios we can go through. We talk about zero fill here, which says we have some bit operand with zeros to become bit operand with HM. Fine, that means I have some number of bits to fill into this larger or smaller number here to make it whatever size it is I want. That's what I was trying to say, right? So I've got some word size in, I've got some number of bits in that I need to set to 0, right? And it usually starts with the most significant bit. So in this example here, right, M was 2, N was 5, right? So I have 2 bits I need to set to 0, and I'm going to start with the most significant bit. So 1 bit, 2 bit. Now it's not bit 0 and bit 1, right? Because that's over here. So I have an in-bit word, in this case 5, so I start with bit 5 and bit 4. So I'm going to subtract 1 from it so I can normalize it to my bit 0. All right, so here's another example up here where I had this 1110101, and I needed to 0 fill it to be properly filling up 16 bits. Okay, so that's what we have. Now, in some operations, we need to LSB the least significant bits first, and you'll see examples of this in your 530 class once you get there. And what that means is that there are some machine instructions that are like half-word instructions. Okay, so I might fetch some value from memory, and it turns out it's going to be an instruction that I need to put into the machine. And if the machine's, in this example, a 16-bit machine, and I only have 8 bits of instruction here, okay, I need to set the least significant 8 bits to 0 so that I don't generate some incorrect instruction and have this machine go off and try to do some divide by 0 or some other silly operation I didn't want it to do, right? So sometimes I need to 0 fill from the least significant bit up. Sometimes I need to 0 fill from the most significant bit down. And those are the 2 principal reasons, the 2 principal scenarios why that needs so. Another operation that we sometimes need to perform in the hardware is that of extension. Okay, this is the case where I want to basically take some number and I need to put it into a larger number. If I took a number from some register, it's a smaller register than a full word, and move it to a full word operation, well, in that case, it would then be an extension. Okay, so I could extend bits one for small numbers, no problem. Okay, if I need to take the negative value, then obviously I would just flip it over using my complement and put that into my 16-bit system instead. Why would I do that? Typically, I would do that with floating point operations. If I need to convert an integer into a floating point number, I typically will do extensions to make that happen. There's an example 107. There's this calculation for two's complement. And that finishes up chapter 3. Any questions on chapter 3?
I have a question.
Yes.
Are you gonna post like certain assignments or like problems we should do, or we should just do them all and do all the ones in the PowerPoint?
Oh, did I not post those yet?
Well, I haven't seen
The
them.
textbook questions?
Yeah.
I didn't post those yet?
For chapter 3?
Yeah.
I haven't seen them. Or maybe you did and I haven't.
I wrote them. Didn't they magically show up in Blackboard? That's possible.
You gave us like 3 problems. Like the thing
No,
was like.
that was in the slides. That wasn't
Yeah.
me. Slides. Let's go. Come on, there you go. Okay, so I need to post that. Okay. I wrote them out. I didn't magically post them. Oh, I know what happened. So I have an Android phone, and I made the mistake. No, that wasn't the problem.
Well, it sounded like that's where you were going.
The problem was I bought my family member one of those other phones. And they had, yeah. She had a problem with it, right? And so I had to spend last night helping her with her problem with it. I got interrupted when I thought I hit upload. I see right now I didn't hit the upload button. So I did work. I did create those questions for me. I know that's a lame excuse, but it really was 11 o'clock by the time I was done with that silly phone.
Did it have an apple on it? Like a little apple?
Yeah, it had an Apple on it.
Okay.
Yeah. Yeah. So you know they have a feature called Do Not Disturb, right?
Oh,
No.
God.
Yes.
Yeah.
Yeah, it
That's
has this
funny.
fun feature called Do Not Disturb. Well, she has a pretty healthy contacts list. And she's getting all these random calls from who knows who, right? So she teaches, doesn't want to get interrupted by some random phone call that's not her contacts. Do Not Disturb does that. Okay, if they're not in your contacts list, it will block those calls. It also blocks all your texts. All texts, including the ones in the contacts. So I was working on that problem. So if anybody has a good solution for that, I'm all ears. But anyway, so I did the work. I thought I hit the upload button. I see right here the evidence is clear that the upload button never got pressed, so I will do that.
You can blame downtime. Let's do that. Downtime.
Okay.
Server maintenance.
What's that?
Server maintenance. Let's go with that.
Server maintenance. No, I like to put the blame squarely where it is. That's just life. Okay, so chapter 3. Any other questions other than the fact that you need some questions to start sharpening your pencils with? No? Yes? Because we had all this discussion on the topics in chapter 3, so we answered all your questions about it. So you're all pretty good with this now, right? If not, then, well, of course, we've got grading assistance and email and stuff like that, too. And discussion board. Okay, so I'll go ahead and turn you loose instead of trying to get started on chapter 4, which